Here are some more examples of predicting the products of E2 reactions. In this top example, we're faced with a cyclohexane ring with a number of substituents. The leaving group, of course, is the OTS. We learned to recognize that as a good leaving group. And there are a number of beta hydrogens. We can draw several of them, and I'm going to label them all HA, HB. There's 3 here. We'll just call one of them HC. And there's one there, HD. And so we can predict some of the products. We know that because this base is not very sterically hindered, we know to expect Zaitsev elimination, where we get the more substituted product. But we can go ahead and write the product that we'd get from subtracting or losing HC as one of our minor products. So let's go ahead and write that in. I'm going to use a different color here. So we know that minus HC should get us to this product. And we know that that's minor because our base is not sterically hindered, but that's still a possibility. As far as drawing the other products, we're going to have to look at a chair structure now because we have this ring structure, and we know that the OTS needs to be axial, and any hydrogen we use to eliminate that OTS needs to be axial in the opposite direction. So I need to draw a decent chair, and then we need to put the OTS in some position. I'm going to use this one. So that's carbon 1. Carbon 2 is right next door. HB is down. HA is up and equatorial. And then this would be carbon 6. Carbon 6 has a methyl that's down, and it has HD up and equatorial. So when we look at this setup, and here's the methyl that we're missing off of the carbon of interest. When we look at this setup, there's really only one hydrogen that's positioned correctly to eliminate the leaving group. And so here is the mechanistic step. We take the CH bond, form a new alkene, and we lose the leaving group. And this gets us to the product up here. By losing HB, we know that the alkene forms between carbons 1 and 2. We still have HA right here. And of course we still have the methyl, and we still have HD, which we don't need to put in, of course, but I'm just going to keep it there. And we know that that's really the only other option we have. The OTS needs to be axial, and HB, or any beta hydrogen, needs to be axial. So we're only going to get these 2 products. HA and HD will never be used in this elimination because they will never be anti-paraplanar to the leaving group. And so we can label this one as minus HB. This will be the major product, and that's because it's, well, in this case they're both di-substituted, but this is more of, we call this kind of an exo alkene or double bond, and this is sort of an internal double bond. This being a di-substituted double bond versus this di-substituted double bond. This one's just slightly more stable, basically because it has substituents at either side instead of only at one side. So there may not be a huge difference here, but I'm still going to say that this is the major product. And maybe it's 55-45, maybe it's 60-40. It's still major and minor. Just understand that it's not going to be a huge difference. It's not going to be 99-1. But that's how we'd evaluate the elimination off of a cyclohexane ring. Now, another thought might be, what if this was our base instead? What if that was our base? We'd have a really large, sterically hindered base, and I think that would just reverse the outcome. That's not going to change which hydrogens can be used in elimination, but it might change which hydrogen is favored in the elimination, and that it's easier to access HC because it's sort of on the outside of the molecule. It's on the outer portion, whereas HB is more in an internal location. So of course we can affect this outcome by changing the size of the base. All right, let's look at this next problem here. This is your standard E2 reaction, and again we have a number of beta hydrogens, and I would say we have 5 of them. And in this case, any of them could be anti-paraplanar to our leaving group. And so we could draw 4 Newman projections from HA, HB, HD, and HE. I'm not going to do that. You can do that for practice. But you should be able to draw 4 reasonable Newman projections, and any of them should get us to a position where we can do this elimination and thus produce, in this case, I'm going to produce the trans alkene, or we'll call this the E. And then I should also be able to produce this one. So this is minus HB, and you can prove that with your Newman projection. This is minus HA. Then, of course, I can do an elimination with HC. And that's not that exciting. There's only one possible stereoisomer that could form there. It's also not as likely as the 2 top products. And then I could lose HD and HE. And this would be minus HE. And then this one would be minus HD. And so all 5 of these alkenes are different. This will be a minor product because it is least substituted. It has a di-substituted alkene. All the rest of them are tri-substituted. This is the E isomer here. This is the Z isomer. And I would say these E isomers are probably going to be the major product. They're both tri-substituted. They're both E, so we could label them both major. And then these Z isomers will be somewhere less than the 2 E isomers, but more than this minor product. And that might be kind of hard to tell, but as long as we can identify which one we know is going to be definitely the minor product, that would be the loss of HC to give us this di-substituted alkene, and which can be the major products. Those are going to be the most substituted E isomers. I think that's really all we need to know here, but it's obvious here there are 5 different possible isomeric alkenes that could form, and you can understand that when we look at all these different hydrogens that are available for this elimination reaction.